number 1, it says write the explicit and recursive rules for a geometric sequence given a table of values. For this first problem, n starts at 0, then goes 1, 2, 3, and then f of n starts at 4, then 8, then 16. So first off, I have the explicit rule and recursive rule formulas written out. The first thing I want to look at for number 1 is r. So r is the number we're multiplying by each time. So to get from 4 to 8, 8 to 16, we're timesing by 2 each time. So that's going to be our r. And then the next thing we need is our initial value a. So the initial value a is 4. So we're going to use a equals 4. And once you have r and a, you're going to plug them into your formulas. So for explicit, we have f of n equals a r to the n if n starts with 0. And that was problem number 1. So we're going to use that formula. We're going to go f of n equals a, which is 4. R is 2 raised to the n power. So that's going to be your explicit rule. And then for recursive, we have f of n equals r, which is 2, f of n minus 1, so that's going to be your equation for your recursive rule. And then for that one, we want to also indicate the initial value, so we write f of 0 equals 4. And then also, because n started with 0, we're also going to list that n is greater or equal to 1. For problem number 2, r is the number we're timesing by each time. So you can see going from 0.1 to 0.3, 0.3 to 0.9. We're timesing by 3 every time. Or you can take the second number and divide by the one before it. And when you do that, you get a value of 3. So r is equal to 3. And then your initial value is the 0.1. So our explicit rule is f of n equals the a value times r, which is 3 to the n. And then for the recursive rule, we have that r is 3 times f of n minus 1. And again, for recursive rule, we're going to list the initial values, so f of 0 equals 0.1. And again, because n started with 0, we're going to write n is greater or equal to 1. For number 3, you can see that n starts at 1, and the terms go 1/16, 1/4, 1/4/16. So sometimes it's a little bit more convenient to look over to the right. But if you look over here, 1 to 4, 4 to 16, you can see that we're timesing by 4 each time. So that's going to be our r. R is 4. The initial term is 1/16. And then we plug them in to the explicit formula. The recursive rule, we have r is 4, so we go 4 times f of n minus 1, and then list your initial term. And then also, since n started at 1, over here we're going to write n greater or equal to 2. On number 4, it says use the formula s of n equals a parentheses 1 minus r to the n over 1 minus r to find the sum of the geometric series. So specifically in number 4, the series goes 2, 6, 18, 54. So each time we're timesing by 3. So our r equals 3. Our initial value a is 2. And we'll plug everything in. Also, there's 1, 2, 3, 4, 5, 6 terms, so n is 6. For number 5, you can see that the terms are going 1 to -3 to +9 to -27. Anytime your terms are alternating, positive, negative, positive, negative. That just means your r is negative. And again, to get from 3 to 9, 9 to 27, you're timesing by 3. So we'll say r is negative 3. The initial value is 1. And then let's count it out. There's 1, 2, 3, 4, 5, 6 terms. So n equals 6, and we'll plug everything into the same formula. So our initial value is 1 minus r. And if we plug this straight into the calculator, I can go 1 parentheses, and you can make a fraction by pressing math right here. And go over to fraction, and then plug everything in. Make sure you get that negative in there. And use parentheses. So you get negative 182. We can also work it out by hand, so I'll do that as well. For number 6, we're going to find the sum, again, of the geometric series, but the problem says, hint, first find n using the formula f of n equals a r to the n minus 1. So for number 6, the first thing I want to do is identify a, r, and n. So a is our first term, so our first term is 2. R is the number we're timesing by every time, so you can see that that's 5. And n is the total number of terms, but that's what we're going to solve for. So to solve it, we're going to use that formula. F of n equals a r to the n minus 1. F of n is going to be the last term, so if you look all the way over, it says 6,250. A is 2. R is 5, and then to the n minus 1. So it's an equation. We're solving for n, so we'll divide both sides by 2 first. And then we want to figure out 5 to the what power is 3,125. So if we check 5 to the 5th power, you get 3,125. And now that we have a statement that says 5 to the 5th equals 5 to the n minus 1, you can set the exponents equal to each other. So you can see that we can add 1. So n equals 6. Okay, so now we can find the sum. So the sum of 6 terms is going to be found using the same formula. I'll also show plugging it in on the calculator. For number 7, the first term is negative 3. To get from negative 3 to 6, 6 to negative 12 to 24, we're timesing by negative 2 each time. And now we're going to solve for n. So we take the last term, 384, and we set equal to ar to the n minus 1. So first step, divide both sides by -3. For problem number 8, it says graph the function and identify the following. So we have 3 to the x. Anytime you have an exponential function, you can always make an xy chart. So for my xy chart, I used -1, 0, and 1. And I'm going to start with plugging in 0. So if you plug in 0, 3 to the 0 is 1. And so I put a 1 right here. And then if you plug in 1, 3 to the 1 is 3. And then if you plug in a -1, 3 to the -1, a negative exponent flips the 3 so that it goes on the denominator, so you get 1/3. And then you can plot those points. So if you go -1 up a third, 0, 1, and then 1, 3, and then you get this curve. So to the right, the graph goes up, and then it creates a horizontal asymptote right here at y equals 0. So domain for this function is, you can see that the graph is not restricted to the left or the right, so the domain is all real numbers, so we'll say from -infinity to +infinity. And then the range, the graph doesn't exist down here. It exists from 0 up, so we would say 0 to infinity. And then finally the y-intercept is 0, 1. For number 9, we have 2 to the x minus 3, so we're going to look at just the 2 to the x graph. So we'll use -1, 0, 1 again. When you plug in 0, 2 to the 0 is 1. When you plug in 1, you get 2 to the 1 is 2. And then when you plug in a -1, you get 1/2. So this is going to be the points on your parent function, 2 to the x. So we'll plot those points. So -1 up a half, 0, 1, and over 1 up 2. So those are the points on the parent function 2 to the x. And now what we're going to do is we're going to take those points and we're going to shift them down 3 according to this transformation. So I actually want to use, originally there's a horizontal asymptote right here at y equals 0. We're going to move that down 3, 1, 2, 3, and draw that horizontal asymptote now. It's at y equals -3. And then we're going to move all 3 of these points down 3. 1, 2, 3, 1, 2, 3, and then this down. So here's your curve. And so that's the graph for 2 to the x minus 3. And domain doesn't change. You're still going from -infinity to +infinity. The range is all values above -3, so we'll go -3 to infinity. And then finally your y-intercept is hitting right here at 0, -2. Number 10, we have -4 to the x. So again, we're just going to look at the 4 to the x first. So I'm going to use the same values, -1, 0, 1 in our xy chart. When you're probably getting the hang of this now, so when you plug in 0, 4 to the 0 is 1, plug in 1, 4 to the 1 is 4, and then up here you get that 1/4 value. So we're going to take those, plot the points, and then there's a negative in front of that 4 to the x. So the negative in front means we're going to reflect these points across the x-axis. So it just moves these points here. And then here's your curve. So there's your graph, -4 to the x. So domain is still all real numbers. Your range this time, the graph is going down. So your range is going to be -infinity up to 0. And then your y-intercept is this point right here, 0, -1. For number 11, it says complete the description of the graph of g. G is 5 to the x minus 6 plus 7 in terms of the graph of f, which is just 5 to the x. So this is your parent graph. And we have g. It says the graph of g is shifted and it says by 7 units. So since the number 7 is at the end, that's going to be up. And then with the x, you have x minus 6. So since that number is with the x, that's going to be a right or left shift, but it's minus 6. So we're going to go right by 6 units. Number 12, we have f of x is a to the x, and then g is 1/2 a to the x. So in front, you have a vertical compression, and it's by a factor of 1/2. And then number 13, we have -5. So we have a vertical stretch by a factor of 5 and reflects across the x-axis. For number 14, it says graph the given function and identify the following: domain, range, and y-intercept of f of x. So for 14, f of x is 1/2 to the x minus 2. So we're going to work with just the parent graph of 1/2 to the x. And let's make an xy chart. So when we plug in -1, 0, and 1, 1/2 to the 0 is 1, 1/2 to the 1 is 1/2, and then when we plug in -1, and when we plug in the -1, we get 2. So we're going to plot those points for the parent function. So -1 up 2, 0, 1, over 1 up 1/2. And then our transformation is we're going to shift everything down 2. So remember on this graph, the parent graph would go something like this, and it has a horizontal asymptote at y equals 0. So we'll shift that first, the horizontal asymptote down 2. And then we'll move all these points down 2. Okay, so here's the graph. And the domain is all real numbers. The range are all values above 0. The range are all values above -2. And the y-intercept is 0, -1. For number 15, we have 1/3 to the x minus 2 plus 1. So in here we have a parent graph of 1/3 to the x, and then we have 2 transformations. Up here the number is with the x, so that means we're going to move right and left, but because it's -2, we'll shift right 2. And then this plus 1 will shift the graph up 1. So let's work with the parent graph 1/3 to the x. So 1/3 to the 0 is 1, 1/3 to the 1 is 1/3, and then the negative exponent will reflect it to 3. So I'm going to plot those points. And we're going to move these points on the parent graph right 2 and up 1. So I'm going to put the horizontal asymptote up 1. And again, we're going to move these 3 points right 2, so 1, 2, and up 1. So we'll move this point right 2, 1, 2, and up 1, and this point right 2 and up 1. So there's our graph. Domain is all real numbers, again because the graph isn't restricted to the right or the left. Range are all values above 1, so we'll go 1 to infinity. And the y-intercept. To find the y-intercept, we're going to plug in 0 for x because you can't see it right on the graph. So we'll go y equals 1/3. We're plugging 0 in for x. So you end up getting 1/3 to the -2, so 1/3 to the -2. And so the negative exponent flips the 1/3. So now it's to the power of 2, and you get 9 plus 1, or 10. So our y-intercept is 0, 10. For 16, we have f of x equals -1/4 to the x. So the parent function is the 1/4 to the x. So 1/4 to the 0 is 1, 1/4 to the 1 is 1/4, and the negative exponent flips the fraction, so it's just 4. we have a negative in front, so that reflects across the x-axis. So we're going to reflect these points across the x-axis. And there's your graph. And you have a horizontal asymptote at y equals 0. So the domain is all real numbers. Your range, the graph is from negative infinity up to 0. And the y-intercept is 0, negative 1. For number 17, we have g of x equals 1/4 to the x plus 5. The transformation has a vertical translation up by, and then we're going to look at the number at the end, so that's 5, so we say 5 units. This is an exponential graph, so the domain is all real numbers, so we'll go negative infinity to positive infinity. And then the range, you're going to look at the number at the end, so that plus 5 indicates that the range is going to be y such that y is greater than positive 5. Number 18, it says the transformations are a reflection across the x-axis and a translation right by, and we're looking up here, and it says x minus 2, so it's right by 2 units. The number at the end tells us how the graph is moving up and down, so we're going to go down by 4 units. Still an exponential function, so our domain is negative infinity to positive infinity, and the range is y such that y is less than, this time it's less than because it was reflected across the x-axis, so we're less than negative 4. For number 19, the transformations are a vertical stretch by a factor of, and we're looking at the number in the front, so it's a factor of 3, and a translation left by, and we'll look up here at the exponent, so it's a positive 9, so we're left by 9 units. And then finally up by 8, so the number at the end tells us how far the graph is shifting up. Domain still negative infinity to positive infinity, and the range is all values y such that y is greater than 8. All right, so this time we're looking at the graph of e to the x, and we need to identify the domain. So domain, it's still an exponential function even though it's e raised to the x. So your domain is still negative infinity to positive infinity. Because there's no number at the end, so it's like e to the x, and it doesn't say like plus or minus over here, the range is y such that y is greater than 0. And let's just give ourselves a little mini graph of e to the x. So e to the x hits at 0, 1. So we can see this is our little mini graph of e to the x. So as x approaches negative infinity, that would be to the left. The graph is approaching a height of 0. So the height f of x approaches 0. As x approaches positive infinity, so that means to the right, the graph is going up really fast, so we would say positive infinity. And then the graph of f of x does not have any x-intercepts, but has a y-intercept of, and this is 0, up 1. For 21, it says you invest $500 at 3.25% compounded quarterly. How much money will you have after 15 years? So first, I'm going to make a chart. So we'll go P, R, N, T. So P is the initial investment. So you have 500. Our rate is 3.25%. So this is your percent. So your decimal is moving the decimal 2 to the left. So it's 0.0325. N is the number of times that the investment will compound per year, and it says compounded quarterly, so that means N is 4. And then T is the total number of years that you're investing this amount. So how much money will you have after 15 years? So T is 15. And we're going to plug that all into our equation. V equals P times the quantity 1 plus R over N to the NT. So we'll plug everything in. So you get $812.52. So $2,000 is going to be our principal. It says 8.32%, so we'll move the decimal 2 to the left. It says compounded annually, so annually means that n is 1. And then how much money will you have in 10 years? So there's your t, and we'll plug everything in. So 4,447 and 51 cents. If you invest 1,500 in an account that earns 3.1% compounded monthly, how many years will it take for your investment to reach 5,000? So we're going to still use the same formula. So you invest 1,500, so that's your principal. The account earns 3.1%, so we'll move the decimal over 2. It says compounded monthly, so monthly would be 12 times per year. How many years will it take for the investment? So we're trying to find time. And then investment means that your value is going to be 5,000 at the end. So we'll go 5,000 equals the 1,500. Okay, so we're going 5,000 equals 1,500, and then here's the formula where everything's plugged in, and we're solving for t. So I'm going to press y equals on the calculator, and then I'm going to type in the left side of the equation, which is 5,000. And then in the y2 position, I'm going to type the right side of the equation. And then where it says t, I'm going to put x. So where it says t, I'm going to use the button right here, which has the x on it. So then you select that, and it gives you your variable. So we're going to go ahead and change the window on this. So if you use the window button, which is right here, we want something for y max to be bigger than that. So I'm going to write 5,100 and then hit graph and see. We're probably going to have to adjust a little bit more to get the picture in the viewing window. But you can see there's the 5,000, which is this side. And then let's see if this graph is actually going to make it in our viewing window. I'm guessing it's not, so we're going to probably have to change the x max to be a lot larger. Okay, so there's the 5,000. And then you can see the pink line is indicating the graph that's on the right. So we want to find where those two graphs intersect. Second calc, and then we'll go down to intersect. And then it says first curve, then second curve, and then enter. And then right here is the intersection. And we're going to look at the x value. It says 38 point, and we'll round that 8 to a 9. So after 38.9 years, that's when the investment will reach 5,000. For 24, Madison invests $400 in an account that earns 4.25%, so we'll move the decimal 2 to the left. And it says annual interest compounded semi-annually, so n is 2. Find when the value of the investment reaches 3,000. So we're solving for time, and then our value is 3,000. Okay, on the calculator, we're going to type in the left side of the equation, which is 3,000, and then y2 will be our right side. And before we hit graph, we're going to change the window, so let's press window. On window, our y max is going to be more than 43,000. So the intersection is occurring at 47.9 years. For 25, you invest 600 in an account that earns 5.2% annual interest compounded continuously. Find when the value of the investment reaches 3,500. So this time we're using V equals PE to the RT. The amount we're investing, 600, is our P. The 5.2%, we're going to move the decimal 2 to the left. It says find when the value of the investment reaches 3,500, so we're solving for T. And we're going to go 3,500 equals, and we're going to plug these values into the right side of the equation. So 600 E to the RT. We'll put 3,500 as our Y1, and then our right side is 600. There's the E button, 0.052, and then X. So I'm going to take the window, and I'm going to make the Y max. Take the Y max to be 3,600, hit graph. For 26, it's an exponential function, so we're using f of x equals c naught a to the x, where c naught is the initial value. So it says in 1985 there were 285 cell phone subscribers, so that's our initial amount. So we're going to plug that in for c naught. And then because it says the number of subscribers increased by 75% per year, we're going to move this decimal 2 to the left, and so you get 0.75. And because it was increased, we do 1 plus 0.75. So that's our A value. We're going to plug that in right here. And then we still have to the X. Then it says how many cell phone subscribers were in Centerville in 1994. Going from 85 to 94, that would be a total of 9 years. So we're going to plug in 9 for X. So we plug in 9 for X, and then we're going to get an answer on the calculator. So we get 43,870, and we'll round that to 2 people. Bacteria multiply at an exponential rate. A specific type of bacteria splits into 2 new cells, thus doubling. If initially there is only 1 bacteria, so initially there's only 1 bacteria, but it's doubling every day, so that means our A value is going to be 2. If it was tripling, our A value would be 3 raised to the X. How many bacteria will there be by the end of 1 day? So 1 day has 24 hours, so we're going to go F of 24. And we're just going to plug 1 times 2 to the 24th power into the calculator. A lot of bacteria. An adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in the person's system decreases by about 29%. So I'm going to move the decimal 2 to the left. And because it's a decrease, we're going to go 1 minus 0.29. And so you end up getting 0.71. That's going to be our A value. So we'll plug this all in. F of x equals, and again, initially there was 400 milligrams. And our A value is 0.71. It says how much ibuprofen is left after 6 hours. So we're going to go F of 6 equals 400 times the quantity 0.71 to the 6th power. And we'll plug that into the calculator. You get 51.2 milligrams.
In your eyes, the light, the heat.